Before beginning my presentation, I want to extend my thanks to Professor Emmanuel Ferrier and his colleagues for inviting me to this excellent event. And also I want to thank to Maurizio and Thanasis because they have already summarized the basic background of the subject. So I'm going to try to focus on the experimental work that we carried out. And my colleagues that helped during all the preparation of these presentations, Mr. ERKAN, Mr. Cömert, and Dr. Cem Demir. I should also acknowledge them. In the content of my presentation, I will make a brief introduction, and then, again, kind of a similar pattern to Maurizio and Thanasis, I will share with you some experiences that we had on FRP confined concrete, and then retrofitting of substandard columns with FRP confinement. That's very important for Turkey. I mean, the word substandard is very important for Turkey because we have a lot of existing structures in a lot of big cities, and unfortunately, a very great majority of these structures are substandard on all aspects. Concrete quality is poor. Poor means like 10 megapascal compressive strength in average, which means that we have 7 megapascal, 6 megapascal concretes in many cities. Plain bars, poor detailing, and so on. You can see any kind of structural problem in existing structures. The problem is that seismicity is much more severe than France and all the rest of the Europe. So we expect earthquakes, severe earthquakes, which could cause significant casualties and significant damages. So that's very important for Turkey. And I should say that in Turkey, there are seismic codes from very old times. Some of the recent codes were published in 1998, just before 1 year before the great earthquakes we experienced in 1999. And then 2007, we revised the code. And the new code will be published within 3 months, probably, which is about 500 pages on just seismic design code, which includes seismic safety assessment of existing buildings, as well as seismic retrofitting. These two parts were added to the seismic code in 2007. I should say that the constructions are much better now, but the problem is that most of the structures were constructed in 70s, 60s, 80s. People are living in those buildings, so they need retrofitting. And unfortunately, the government doesn't look at the retrofitting issue very nicely. They prefer demolishing and reconstruction, which is always not possible. So still there are many structures that should be retrofitted. And FRP is generally a good option where the owners of the buildings are more happy because of the relatively less disturbance to the occupants. So most of our studies have been focusing on substandard structures, which represent existing structures in Turkey and probably in many places, probably in Italy, I guess, some parts of Italy, maybe in, I don't know, Greece, Balkans. I believe there are similar structures like that. Then I'm going to talk about improvement of cyclic flexural capacity of substandard RC columns with FRP reinforcement. I was happy that there are some works already going on these issues by the private sector, Fresina and other companies. And then I'm going to talk about retrofitting of reinforced concrete beam column joints, and then behavior of retrofit of historical masonry structures, which we have a lot in Turkey. And then I'm going to summarize some works that we will carry out on full-scale real buildings of 3-story within 1 month probably. I was hoping to show you the results of this test, which are specially built 2 structures, 3 stories on field, and they will be tested at the same time. One is retrofitted with FRPs, the other not. All same characteristics. But unfortunately, in Turkey we experienced very strange things like coup, etc. last month. So we couldn't complete the test as we have planned. Therefore, I'm just going to show you some preparations and some theoretical aspects of this study. So little bit on confinement. As you see, that's a great problem, even though we have good spacing, I would say, but poor hooks here. In many cases, spacing is much less or much higher than this one in Turkey, like 20 to 25 centimeters. Yesterday, the analysis mentioned that if you have stirrups with 25 centimeter spacing, you shouldn't consider that as confinement. It's correct. And in many cases, the details are also not good enough to consider them as real confining reinforcing bars, because the angle is not 135 degrees, but just 90 degrees. And the hooks are very small, which you can never get the anchorage. So almost they are like unconfined concrete, which means that you have no ductility, which is vitally important during an earthquake. Therefore, we began the work using confinement, but unlike the usual works carried out in literature, they were relatively larger scale specimens, and they generally included reinforcing bars inside to represent the actual situations in a more realistic manner. And we tested many different types of sections, many different types of concrete strength, many different types of fibers, hybrid fibers, pre-damaged cases, cyclic loading, etc., etc. I'm not going to spend too much time because you already heard about this. So generally it's told that confinement is very effective in case of circular sections, but obviously you see here, these are cross-sectional aspect ratios, circular, square, 1 by 1, 1 by 1.5, 1 by 2, and 1 by 3. Codes were limiting these cross-sectional aspect ratios to 1.5 until very recently. In Turkish code, seismic code, it was limited to 2 based on this work. But now we see that we can even apply these when the aspect ratio is like 3. Because even though it doesn't increase strength significantly, it has substantial enhancement in terms of ductility, which is much more important in case of seismic issues. I mean, that's the main issue in the earthquake. You need ductility. Because particularly if you have a low quality structure, it is impossible to resist seismic forces with your strength, but what you can do is only to increase the ductility. So this was a very good news. And I'm going to show you some results on larger scale columns, which were subjected to reverse cyclic lateral loads and vertical loads as well at the same time. We got some similar results. So although these results are for basically concentric compression tests, we got very similar results on very large scale columns as well. Hopefully I'm going to show those to you. And we examined different effects, loading rate, different types of concrete quality. Of course, there's a good news about bad situation. When you have low quality concrete, firstly, your concrete is more ductile. I mean, 7 megapascal concrete is more ductile than 30 megapascal concrete. And also, you can improve your behavior much more easily by using FRPs with respect to high quality concrete. So that's kind of an advantage. Here you see, for example, 7 megapascal concrete wrapped with FRPs, and here you see 30 megapascal concrete wrapped with FRPs. You see that improvements are significantly different. So it's always more difficult to enhance the behavior of a good quality concrete rather than a poor quality concrete. In these graphs also, the loading rate was studied. And obviously, interestingly, when the loading rate is low, we had higher deformability, very probably because of the creep of the concrete during the loading. But again, this was different when the concrete quality is different. You cannot always say that loading rate is very effective on the behavior. It depends on the section shape, it depends on the concrete quality as well. About creep damages, this is a photograph from a kind of high-rise building, 12-story or something like that, east part of Turkey. These damages didn't occur during an earthquake. This occurred during vertical loads. Sometimes some structures collapse under vertical loads in Turkey. Rarely, but it happens. Without any extra load, without any ground movement, settlement, etc. Very probably because of creep effects. Therefore, we carried out many works on long-term loading to see the creep effects and how we could improve the behavior under creep, under sustained loadings. And I'm not going to go to details of these numbers, but basically I could say that you could significantly increase the creep performance, or I could say that you could enhance the performance under sustained loading significantly. Why this is important? Because as I mentioned that, since in Turkey, concrete quality is around 10 megapascal, whereas during design it was considered as, let's say, 20 megapascal. So normally in design, axial stress on the column is, say, 0.3 or 30% of the axial capacity. But in real life, it is 60% or 70% of the capacity, sometimes more. Therefore, creep is a significant issue, important issue, and a common issue. So you have somehow to improve this situation, to avoid this kind of failures, even under vertical loads. So this works as well in these cases too. I'm not going to enter in details, but I think you should have noticed yesterday when you confine the section with FRPs, in case of rectangular sections, you have to round the corners to avoid stress concentration. Otherwise, you may have premature failures. This graph clearly shows the effect of the corner radius, where we have 40 millimeter, 20 millimeter, and 10 millimeter corners rounded. You see, obviously, the behavior is different. So there are a lot of models, as my colleagues mentioned yesterday. But if you don't consider, for example, this simple effect, you could end up with significantly different results. It's a small detail, but very effective on the behavior. I have mentioned that the concrete quality is important. When you have lower quality, the enhancement is much higher. And if you compare these two, cyclic loading and monotonic loading, they are identical specimens. The behavior is almost similar with some marginal differences, which is again a good news for the type of earthquake loading. And also we had many tests for determining the combined action of internal steel reinforcement and external FRP wrapping. It wasn't always like this type of scarce transverse reinforcement, but we had also frequent reinforcement situations as well. So I can, as a summary, say that you could think about the contributions of internal confinement and external confinement and sum them up, and you go to a reasonable situation. So you can simply determine the confined concrete characteristics within the core using any model, say Mander model or any confined concrete model. And also you can consider the whole section using the external confinement, and you come up with a rational result for that. And with that, I complete the concentric compression test, and I want to go ahead to retrofitting of substandard columns, of large-scale columns with FRP confinement. There are some tests for shear. Yesterday, my colleagues mentioned that obviously we have a significant increase in shear. But what I have mentioned to my colleague from France was that, for example, these columns are retrofitted in shear using different FRPs. This is theoretical flexural strength. So even though the number of FRPs increase, you can never exceed a certain value because there's a risk of diagonal compression failure as well. So you should have a margin. I mean, if you have already used a lot of transverse reinforcement, it may be irrational to use some more FRPs because diagonal compression failure may be an issue. Anyway, you may have, this depends on your situation. If you are lacking of transverse reinforcement, yes, you can increase your shear capacity. These are another group of tests that we made retrofitting of potential plastic hinge regions of columns using FRPs and other different types of jackets. I'm just going to show you a FRP case. Again, my colleagues mentioned that you could improve the lap splices. So these two groups are representing two different types of specimens. In this group, there is no problem about lap splice. But the problem is about lack of sufficient transverse reinforcement. So the reference specimens behave quite brittle manner. The formation capacity is very low. And when you wrap them up with FRPs of different thicknesses or different application details, you can reach the theoretical flexural strength, so that's what we want. But in case of deficient lap splices, in this case, where we used plain bars, the improvement is not as significant. I should say that this case, when the plain bars are used, there is no hook at the end of the lap supplies. Of course, normally you should have this lap supplies, but there are many cases where the lap supplies is not, the hook is not applied at the lap supply. So if you think that the Eurocode equations may be valid also for plain bars, that's totally incorrect, because the external transverse deformation, which would lead slip of plain bars, is much less with respect to deformed bars. So this kind of lap supplies deficiency in case of plain bars without hooks would not work. Only small enhancement in the behavior could be obtained. This is another group of specimen, quite large scale. The section is 30 centimeter by 60 centimeter. The PhD is going on. There are different sections with cross-section aspect ratio of 1, 2, 3, and 4. So we are testing rather full-scale specimens like that to whether we can extend the existing equations, existing approaches for larger scale specimens as well as larger ratios of aspect ratios. And the tests were carried out in two directions. On the strong axis of the column, so the lateral load is in the direction of 60 centimeter depth, and also in the weak direction of the column, which is more critical because we don't have the cross ties. When you have the FRP, it's good in strong direction because the compression part is quite close to corners where you have good confinement. But during loading in weak direction, you may need cross ties. So we checked these situations, but nevertheless, the results were quite good. I mean, we used also external cross ties to improve the situation, but even these are fresh tests. I don't know I included them in this presentation or not, but even though I don't use cross ties for this 1/4 section in a weak direction, we still got quite good experimental results in terms of ductility. If you look at the failure of this specimen, which is, as I said, 30 centimeter by 60 centimeter and loaded in strong direction, and axial load is quite high, I should say that. There were different levels of axial load, but this test, I believe, was under 35% of the capacity of the column. So keeping that load, we applied reverse cyclic loads. So as you see here, the reference specimens without retrofit were damaged significantly at 1.5%, and significantly losses axial load capacity at 2%. When we retrofit the column with 1 layer and 2 layer of FRPs, you can see that the specimens could suspend the lateral loss up to 5% drift, which is quite good enough for even high seismic zones. So significant improvement was obtained, and this shows the load displacement graphs. You can see both the drift ratios and displacement values here, load values here, and the drift ratios are here. So that's the reference specimen. As you see, a behavior that you wouldn't like to have. And then after retrofitting, you have this type of behaviors, and this shows the comparison of the envelope curves of these load displacement diagrams. So absolutely we could go to which we wanted to go. And this shows two specimens tested in the weak direction, where FRP might be not equally effective because you don't have the cross ties. But still, as you notice here, the ductility is improved with respect to reference specimen. Not much, but again, better than reference specimen. So another issue which is quite new, relatively new, improvement of cyclic flexural capacity of substandard RC columns with longitudinal FRP reinforcement. I mean, flexural retrofit has been done for beams, span sections of the beams for a long time, but not for the columns where we have moment reversals, and also the anchorage is an important issue to the foundation. So for that, we have been doing different types of, examining different types of details, different types of columns. That's one of the studies. Again, almost a full-scale column. Again, tested under vertical loads and reverse cyclic lateral loads. We tried many details to anchor the column longitudinal bars to the foundation. We used sheets, we used plates, we used rods. We use different types of holes, rectangular holes, conical holes, circular holes. But at the end, we determined that I don't know if you can see it or not, but when we have to open a large hole, not like a driller, but a large hole with breaking the bottom part of the column, and use a good grout and put the rod inside. Otherwise, we always had difficulty because it's very difficult to do this properly using a normal workmanship on site. If you try to put epoxy inside a drilled hole, at least we couldn't manage this, although we paid a lot of attention. So practically, I think it's not possible to have good result by drilling a hole and trying to anchor it inside. So with that, there are some applications here. This was an interesting application actually, because that's not like external bonding. That's also not like near surface mounting, because in Turkey, generally for these old type of structures, we have also corrosion problem. And since concrete quality is poor, what we have to do is generally take out the concrete cover to clean the rust. And you have to do this also because there are a lot of cracks already on the column. So when you remove this, it's also good because you can have a better cover concrete with a better repair mortar, and then put the reinforcement, FRP reinforcement, and make cover again using a good, better quality repair mortar, and then wrap it in transverse direction to avoid shear failure, because you increase your flexural strength, which means that you may be in trouble in terms of shear due to capacity design. So you also have to use transverse reinforcement using FRP sheets. This graph shows different, the envelopes of different load displacement curves. These are reference specimens. These are some different type of anchorages to the foundation. As you see, there's a kind of improvement, but you lose this at an early stage because of the problems in the anchorage, because of localized problems in some parts of the anchorage. But when you properly anchor the rod to the hole that you opened in the foundation, you could go both very high strength, which is, I mean, too high maybe in this case, but also more importantly, the drift capacity that you sustain this load is more important. So then you have a much more proper behavior. If you look at the joints, which are often problems in the corner members, I think yesterday one of my colleagues mentioned that if you have good columns, joint may not be that important because you have the slab, you have the transverse beams framing into these joints. But in the corner joints, the situation might be a little bit different and might cause significant problems, where, as you see here. So we tested large-scale, full-scale columns or sub-assemblage, and you will see the three-dimensional frames to examine this behavior. And I just want to remind you three types of failures I'm going to talk about, which is J-type failure, which is the shear failure of the joint. The other is SJ-type failure, which is a slip of longitudinal bars of the beam within the joint, and then failure of the joint. And B-type failure, which is we want. Joint doesn't get any damage, but beam fails due to flexural mechanisms. So I will show you three specimens of different arrangements, how we obtain these three kinds of failures. These are the joint specimens tested. About 20 specimens were tested like that. They are full scale. The columns are 25 by 50, and the beam is 25 by 50. And also we have a same dimension transverse beam and a slab of 8 centimeters. Often joint tests are carried out without this transverse beam and the slab here. Therefore, I think there are two problems about this type of test. One is you underestimate the performance of the joint, existing joint, because you omit the transverse beam and also the slab, which has obviously some effect on the shear performance of the joint. And secondly, you overestimate the effect of retrofit, because you can easily wrap that kind of a joint, whereas you will not be able to do that in practice because of the presence of the slab and the transverse beam. You see that, so this is the specimen, as you clearly understood, this is the column, horizontal, this is the beam. And as you see, there is no reinforcement within the joint core. This was the actual practice in Turkey until 1999 earthquakes. No joint, you cannot find any joint reinforcement. So this is the testing setup. We had axial load of different levels from 10% to 50%, even more than 50%. These are some measurement details. This is the loading pattern, displacement controlled. And this is the behavior of reference specimen. Hard to decide is good or bad. This is the theoretical flexural capacity. In this specimens, beams are weaker than columns, but joints are weaker than the beams. So critical part is the joint. I don't know, how do you evaluate this one? This is not too bad, I guess. Because even though the capacity is less than anticipated during design, the joint can sustain its capacity until 4% drift. Through a mechanism which we never considered during our design. What happens is that under reverse cycle loading, the beam longitudinal bars hooked into the joint causes crashing of concrete in front of the hook. Therefore, the bars slip out before it reaches its yielding stress. So the capacity is less. However, due to this unforeseen slip type of behavior, we have a kind of pseudoductile behavior. So you don't lose the strength, unlike shear failure. So interestingly, if everything was as we wanted, so there was no slip, there would be shear failure, which is much more brittle than this one. So anyway, but still this is not the thing we want. But you should consider this during actual life. When you make design, okay, I'm going to wrap it. No, it will not work because there will be shear failure and your FRPs probably will not work in such a case, for example. So firstly, this problem should be solved. By the way, I should highlight this point. You see the main crack is here on the beam, just at the interface of the beam and the joint. Of course, there were some shear cracks because the hook of the longitudinal bars were going out, therefore crashing the back part of the joint. And also there was some shear cracks, but main damage was the crack at the interface, which is basically due to slip of longitudinal bars. So this explains this kind of mechanism. This is the damage, and this is what happens to the longitudinal bars. So main crack here, and also some damage here because of the hook deformation, and also some shear deformations and damages. So if you directly apply FRP, you don't get any change. I'm not going to show the result here, but we tested it as well. So this specimen, you wrap it up with FRPs, nothing changes because slip occurs again. So you gain nothing. You do a lot of things, gain nothing. So first, you should somehow avoid this kind of slip of longitudinal bars, which is not easy. What we did was, we removed back part of the joint. You can do that because there's a corner joint, as I mentioned. So you can go up there and clean the cover concrete. And on top of that, we went just in front of the hooks, so behind the hooks, and we changed the concrete there with a better quality concrete, which is kind of repair mortar. So now, in front of the hooks, you have a better concrete which could resist compression stresses. And also, we just welded the hook of top bar to the hook of bottom bar. So therefore, we hope that we avoided the slip, and we really did. As you see, we could reach much higher strength, but then the shear failure occurred at this strength level, so we had a brittle failure. Now this is better specimen to see the contribution of FRPs, because we want to avoid shear failure. And then we retrofitted such joints which fails with shear failure using different configurations of FRPs. Note that these are totally applicable details because these represent the real assemblage, totally. Just you have to do is just remove some part of the wall here and here. And there's no anchor, there's nothing, just you wrap the joint and the column, that's it. No drilling and no bonding into the drill holes. And what we come up with is such a behavior, which is B-type failure. So we didn't have any damage on the joint, just saw small cracks. But the main failure was due to the bending of the beam at the yield capacity of the beam. So we have reached the target. So here you can see the damage of the beam flexural failure. If I go one back here, you can see the total shear damage here. In this case, we didn't have any slip cracks, but we just had the joint shear crack. So we wanted to verify this in larger scale specimens. As you see here, these are full scale specimens, just representing the half heights of the top story and half height of the bottom story, but all the sections and dimensions are full scale. Again, we had different levels of axial load. I'm going to just show some tests because they were all almost similar. The loading was a little bit different. We applied Düzce earthquake record. We just analytically calculated that and then applied it in a quasi-static manner to the specimens. I don't want to repeat all, but basically what we obtained was quite similar. Again, slip in reference specimen at much lower strength than theoretically considered if you ignore slip. And then kind of shear failure, brittle shear failure, if we avoid slip through welding and replacing the poor quality concrete with a good mortar. And then we obtain the behavior we want using the FRP retrofits. And I'm not going to repeat the damages here, but these are very similar to damages that I have shown in the previous tests. And these are the envelope curves, which clearly summarizes what I mentioned. If you look at the historical masonry quickly, we have a lot of these types of building, 200 years old, 300 years old, 100 years old. Towards that, we made many tests, like this kind of diagonal tension test. Generally, we use real bricks taken from the original structures, which are demolished somehow. And also we use the mortars which replicate the historical mortars. We use different types of FRP, different types of configurations, different types of anchorages. And at the end, we always see the significant contribution of the FRP retrofit, particularly if you are successful to avoid premature debonding of the retrofit system over the surface. And also we tested specimens using textile reinforced mortars, using open grid basalt mortar composites. We made tests, diagonal tension tests, as well as axial compression tests on different aspect ratios of the sections. And again, we had obtained quite good results in an expected manner. So I'm going to pass those quickly. If you have questions, I will try to answer at the end. This shows the axial loading test results. So now I'm going to show you a full-scale test we carried out on site. We finished this several years ago, and you can see many details on this web page. Also in YouTube, you can see a video, a kind of documentary of this study within 14-15 minutes. So we tested a real building, a part of real building on site, 3-story. And since this building was quite good than many examples we see in practice, concrete quality was a little good, and it had a strong column, weak beam configuration, which is rare. So we built another structure here, replicating the characteristics of existing structures in a more realistic manner. Lower quality concrete, strong beams, weak columns, and we tested both these two structures. This has nothing to do with basically FRPs, but just that's an interesting example that I want to share it with you, and maybe some videos may work, I don't know. What I could say is we had totally different failure mechanisms than anticipated. You can make detailed theoretical analysis, but in all cases, we had significantly different behaviors. For example, in this building, we had buckling of beam bars, buckling of column bars. So if you don't consider buckling, normally you don't, when you make an assessment, normally you don't take into account the buckling of bars. So you totally go up with a different result, totally different. And the second case, the video is not working, I'm sorry about that. It was interesting to see all the building moving to the dirt, 4% drift. And the second, we had a slip of longitudinal bars. Again, you totally different mechanism than you could do using ASCE 41 or Eurocode. We are talking about core rotation limits, but everything is going on a different way. when you are talking on a substandard structure. So this was very surprising for us to see, even though we had experienced that on individual columns. To see in a structural scale is quite different. At the same study, we also carried out some dynamic shaking tests using shakers and some accelerometers at different damage states. So we pushed and pulled the structure to 1% drift and removed the actuators and make shaking and measure dynamic characteristics and different levels to go to a relationship between dynamic characteristics and damage level. Anyway, the final issue I'm going to talk about is the large-scale test we plan to do in near future, probably next month, in a city close to Istanbul. These two structures are just constructed for this purpose. So two almost real structures you see. And this one is now retrofitted with FRPs, columns. I'm going to show you some issues about design of the retrofit. And this is as is. You see some weights over the building to represent live loads, etc. And they will be tested at the same time, which is quite a difficult work. And this is expected to collapse. And they want us to collapse the building. And I'm going to show you that we expect collapse like 1% drift for this structure. But since this structure is wrapped with FRPs, probably it will go to 4% drift. I don't know, we are going to see that. Theoretically, it will go. This is the plan of the structure and 3D appearance and elevation. And it represents existing structures in Turkey, which means that we have strong beams, weak columns, we have poor details of columns in terms of confinement, etc. Some photographs from the construction and some information here. Some details of the columns. Now we have joint reinforcement here because we didn't want to have a confusing failure mechanism. We just wanted to have the failure on the columns. So the joints were well reinforced. And beam details and foundation and construction stages, the walls, and some theoretical analysis to see what kind of behavior we are going to obtain for the reference specimen and the retrofitted specimen. So that's the pushover curve or capacity curve of the reference specimen, where you see that, where you cannot see actually, but the drift is about 1% here. So, I mean, that's prepared in MAC, so there's some incompatibility probably, so you don't see here the drift ratios. But I could say that we expect failure at about 1% drift, which is not good enough for a good seismic behavior. And what we expect is, first we will have flexural yielding, and then with increase of deformations, we also expect some serious shear problems in the column, and then we will have axial load collapse of the columns. Quite sophisticated analyses were carried out for that, but I'm not going to talk about the details. But what should be emphasized is there will be problems about flexure, there will be problems about shear in reference specimen, and also axial collapse is expected to occur. So for the retrofitting, we wanted to increase the ductility, therefore we increased the ultimate compression strain of concrete to 1.8%, at least theoretically. The theoretical target was that. With that, we come up with 5 plies of carbon FRP wrapping of the columns. We could reduce that, still it would be good, but since there's a kind of demonstration test, we didn't want to have any problem. So then we totally avoided the shear failure. Also, we retarded the flexural failure significantly because of the increased ultimate capacity of concrete in compression. And then here, the unconfined concrete behavior, that's FRP confined concrete. And these are the lateral load drift ratios for the reference specimen and the retrofitted specimen. Of course, these are theoretical, and we are going to see what is going to happen in the field. So the retrofit scheme is like that. For shear, we had, that's for the ground floor, that's the first story, or this first and second story. we have the 2 plies of FRPs for shear throughout the column height, and for getting improved ductility at the maximum moment zone, plastic hinge zones at the top and bottom parts of the columns. 5 plies at the ground story, and the 3 plies plus, this is total 3 plies, 2 plus 1, and here 2 plus 3, 5, to avoid brittle failure of the plastic hinge zone. And this shows just the detail of how we wrap it, and some photographs from application of strengthening works. Test setup, I'm not going to enter into details. Measurement system, this is already on. I mean, we would do the test, just this coup happened before this coup event had happened. So we hope to execute the testing hopefully at the beginning of October. So I'm very excited to see what kind of behavior we are going to obtain. Just one last example, which might be interesting if the videos work. We also made some tests on impact for improving of impact resistance, because what we saw that these are good quality concrete members, concrete columns with axial load on them, all complying with the codes. When you load it statically, like a car hit to the column, one of my colleagues has shown, you have a flexural type of behavior. But if you apply to the same point an impact load, the behavior changes from ductile flexural mechanism to a brittle shear mechanism. So if you make a static analysis, everything is okay. You have and the test is also perfect. You have a very nice ductile behavior. But if you apply impact, everything changes. If this works, we will be able to see that. I think it's why it's not flowing. Anyway, I think we came to the last point. This shows the acceleration, displacement, and strains on the reinforcing bars. So I think it's not visible nicely, but there was a very, very severe shear crack. I mean, it's not a crack, it's a kind of very, very bad failure. So when we retrofitted with FRPs, probably this will not work as well. Let's see. No, it's not working. Anyway, the shear failure was totally avoided, and we just got a much, much improved behavior in terms of flexural types of behavior. So for impact type of loading, again, this time we use aramid fibers for retrofit of these columns, but we got a significant improvement on the behavior. I'm sorry that I couldn't show you the videos here. So with that, I want to thank you. I'll be happy to answer your questions.